You will be pausing lots in this video as I've written down the notes, and we're just going to fly through this, okay? Mainly because I'm tired of feeling like I'm making you become bored listening to me write on the smart board. Anyways, to begin, we're going to talk about different models of the universe this time, which is the idea of cosmology, not cosmetology, some of you are saying in class. But we have the first model we're going to talk about is Newton's model of the universe. In this model, the universe is static, which means unchanging, and infinite. Because he described it in both these ways, though, there became a paradox in terms of what the logical conclusions were of having a static and infinite universe. And that was Colbert's paradox, where if we have an infinite universe, there must be an infinite number of stars, so the night sky should be infinitely bright. Obviously, we don't see this, okay? This is a big issue, but we're going to resolve this here in a little bit. The first thing I want to do, though, is tell you that the actual current model of the universe has two very important characteristics that I want you to write down and make like a little box in the upper right-hand corner there on your cosmology page of notes. And the two things I want you to note, the way that we describe the universe today, is that we describe the universe in terms of homogeneity, all right, and isotropy. Okay, so if we took the universe and we cut it into cubes that were 300 megaparsec per side, all right, so that's 300 million parsec on each side. What we see is that each cube looks the same inside compared to any other cube, all right, in general. So that's the first thing. The second thing is isotropy, okay, which basically tells us that if we look in any direction, all right, far enough, we're going to count the same number of stars. So it's distributed the same in every direction, which tells us that something really interesting about the universe, all right, that there is no center to the universe. Additionally, the homogeneity piece here tells us that there's no boundary. It doesn't, change at any point. It's something that we can pretty much take from this. But our universe is finite, and it does not have a boundary, nor does it have a center. Maybe the homogeneity piece we can't connect to the boundary thing, but I think that's the implication. I'll have to get back to you about that in class. So, Colbert's paradox, the quantitative version of this, if we have an infinite universe with infinite stars that are uniformly distributed, all right, we can assume that there's a star density just given by the number of stars divided by the volume. So little n would be the star density. Big N will be the number of stars we're considering, and V is some given volume. So if we consider some number of stars, okay, based on the star density times the some given volume, if we consider some point we're going to be measuring from, why don't we take it as the Earth, as it is in this image in the lower right-hand corner, all right? And let's consider a thin spherical shell some distance d away. The volume of that shell we can just take as the surface area times the thickness of the shell. Now that is, an approximation. We really would have to do the calculus here, but we're just going to ignore that for now since we're not doing calculus in IB physics. At a distance from that star, luminosity L, okay, the apparent brightness we would measure on Earth from that star would be given by B in our formula for apparent brightness. So if we have a certain number of stars in that thin shell, given again what we said, the star density times the volume of that shell, we know that the total intensity is going to be that number of stars times the luminosity, the average luminosity of each of those stars. If we sub in for our equation, our definition of the number of stars in that shell, the density times the volume, we see that 4 pi d squared cancels out. And what we're left with for the apparent brightness of that shell is the luminosity times the star density times the thickness of the shell. So what we have here is a product, okay, of three constants for the apparent brightness of one shell. So it follows, if we have an infinite number of shells with an infinite universe, at constant brightness for each shell, we'll have infinite brightness. Okay, that's our little proof. So we obviously don't have this. Okay, how do we explain this? Well, we explain it in the sense that we have a finite universe. Okay, now the next question is our universe static? Well, Edwin Hubble in the 20s, okay, looked in all directions at, galaxies and whatnot, and we saw that galaxies were in clusters, and they were separated by about 10 megalight years, okay, and there were also galactic clusters that were separated by certain distances. And he was looking at the spectral lines of these galaxies, and what he noticed is that almost all galaxies are moving away from us, okay, all their spectral lines, again, almost, all, except for a few, were redshifted, okay? And so he knew how to calculate the redshift, all right, from special relativity there. And so what he saw, though, was that the further these galaxies were from us, all right, the faster they were moving. In other words, the more redshifted their spectra were. And this is one of the most important discoveries in all of astrophysics. So he studied many galaxies and found that the further away they were, the more redshifted they were. In other words, they were moving away from us faster and faster. So he actually came up with this proportional relationship, which is V equals h times d, or the speed of the galaxy is equal to Hubble's constant times the distance to that galaxy. Okay, so the speed with which they're moving away from us is directly proportional to how far away from us they are. So we actually I have here, all right, a sample spectra, and we can really just use, the lines from our sun as, they're the same for most of these galaxies, since everything is mostly hydrogen, okay? And we see that these lines between both of these spectra are shifted a little bit towards the red part of the spectrum. See, I don't know if you can see in the YouTube video, hopefully, but you can connect and see that these lines are all shifted, same line pattern, all right? Just over towards the red part of the spectrum. As that galaxy, that supercluster galaxies, is moving away from us at 7% the speed of light. And from that, we can calculate that it is 1 billion light years away. So how can we do that? Well, he took all this data, okay, and he placed it on a graph, all right? And what we end up with here is a lot of data that, for the galaxies close to us, fits really well to a line right here, right? This, by the way, it shouldn't be labeled redshift. It should be recessional velocity, but this graph, for some reason, has it labeled as redshift, okay? But in here, obviously, these are moving towards us, okay? A few galaxies within our cluster. But what we have here is some big uncertainty within the Hubble constant. A bunch of galaxies that, as you get further and further away, show us that there is some large uncertainty in this measurement, all right? So the latest value, actually, from the Hubble Space Telescope, and this is old, is actually going to be 72 kilometers a second per megaparsec. All right? So what are some limitations of Hubble's law? Well, enormous uncertainties in measuring distances to remote galaxies, as I just said. That's the big problem, okay? How do we find Hubble's constant? Well, it's the slope of the redshift, I should say, actually, recessional velocity versus distance. All right, recessional velocity being that of the galaxies as they move away. So how can we use this to determine the age of the universe? Well, let's think about it. All right, using the most recent version of Hubble's constant, okay, what we find is that 1 over h gives us an upper bound on the age of the universe. How is this possible? Well, think about it. V over d, which is what that slope is just 1 over time. This is equal to the Hubble constant, based on that graph. So, if we consider 1 over the Hubble constant, we're considering a directly proportional relationship where, when everything was really close together, okay, we're at the start of the universe, all right? When d is really, really close. So when d is really, really close, okay, we are going to be at a point where things are going to be expanding very, very quickly, all right? So what we have here, we can calculate the age of the universe based on this, right? T is going to be 1 over the Hubble constant. So when we substitute our value for the Hubble constant and just do some unit conversions, we end up with about 13.6 billion years. All right, and that is the age of the universe as we have defined it based on Hubble's constant. All right, that's where that number comes from. So an example of a problem that you will have to do, including redshift, is given that we have a spectral line from a laboratory, we know what its wavelength is. We measure that same spectral line from a distant galaxy. You're going to have to calculate the redshift, which is what z is. You can then use that formula, an alternate formula for redshift, z equals v over c, to calculate the speed of that source. Okay, that's the Doppler effect right there. And from there, we get how fast the galaxy is moving. We use that v in our Hubble equation and solve for d, which is the distance to that galaxy. And right there, there's your answer, 760 megaparsec. All right? So that's it for what you need for these notes. If you get the chance, read the chapter 3 from A Brief History of Time. It does a good job of explaining the structure of the universe and its eventual fate. And after if you get the time to read that, that would be good. If not, just organize your notes for the test quiz thing we're having on Friday.